All right, so today's lecture is the last one. So I will give you some other control methods for mobile robot. Yeah, two more methods actually. So before we have, yeah, I have introduced a control method like orientation control for different robots, but in here mostly it illustrated using differential drive wheel. Okay. Um, well, so I have already shown one example how you can construct controller based on kinematic model. Okay. So similarly for other methods, you are going to learn the way to construct controller based on kinematic model. So the next method I'm going to introduce is control to reference pose using an intermediate direction. So first you look at the keyword here. Uh, directions direction represent the orientation of the robot at the desired position at the goal, right? So robot start here. Well, I can say start or instantaneous position. Okay, it can be start anywhere, but the illustration here represent, yeah, to show you that the robot is at instantaneous position and the goal is at this point. So let me put the red color. The goal is at this point. Okay, and the final orientation, the desired final orientation is this one, phi ref. I think I can increase the size a little bit. Yeah. So phi ref is the desired reference at the goal point. Um, and the term intermediate direction means we set up a direction in between. I mean the not to the at the desired point, but in between the current orientation, which is to say this one, and the desired one. So for example here the intermediate direction is this one, okay, represented by phi t. Oh, well, let me remind why orientation represented by vectors like this. Yeah, actually the for example phi given by this direction vector means the angle of this vector with respect to each angle. Okay, this is a representation, just to remind you. So direction of phi t means the angle from x-axis to this vector. Okay. Direction of phi r means angle from x-axis to this vector. Okay. Okay. Now let's see some terminology. First, distance from the instantaneous position to the goal, denoted by capital D. Okay. And alpha is the angle from the reference vector to phi r. Phi r means the angle that we can compute by this vector. I mean from this to this. I can just say vector d. Okay, it just kind of explanation. Okay, so vector d here, it means from instantaneous point to the goal we can construct a vector. So phi r can be computed using like arc 2 of component y of this vector d and component h of this vector d. Okay, and so alpha is a difference between phi r and the phi goal. Okay, phi reference. This is alpha, and then beta is constructed by choosing a fixed r, and we draw a perpendicular line to the vector d, this vector d. So we draw a perpendicular line and choose a fixed value r. So actually, when the robot move to this point to here, d would be like this and r would be like this, or would be like this, and then beta would be here. Okay, if the robot is here. So beta can be computed at time of r over distance d here, and the sign of beta is chosen in the way that it must always have the same sign as alpha. Okay, so we checked the sign of alpha all the time, and then we set the sign of beta accordingly. This is what it means. So in some, okay, not yet, we are going to see the control algorithm soon. And okay, yeah, so when alpha is 0, beta it becomes irrelevant. So beta will not depends on, because if alpha is 0, but beta we compute it by this and this. So it means actually beta here depends on the sign of alpha, but if alpha is 0, then beta is just not relevant to alpha. You can just take any value, plus or minus, it's okay. And then for phi t, because we can compute beta, so we can also compute phi t. Okay, phi t here. So phi t is an intermediate orientation, and so it can be constructed of phi r plus this beta. Okay, phi r from 0 to here, and then plus from here to here, we got phi t. And when alpha, okay, so initially alpha can be very large. For example, if the robot is here, so we can construct a line from instantaneous location to the goal, and then we can have phi r is here. So the alpha initially can be very large, larger than this, right? So when alpha is large, we use phi t as phi r plus beta. But when alpha drop to be the same as beta or smaller than beta, we switch to be like this. Okay, because when alpha is too large, um, instead of using phi reference as phi goal, we use phi t. Oh, okay. So actually, alpha constantly change. I mean, continuously change. So here is the switch. How we can make condition to switch. Just whenever alpha, absolute value of alpha is less than or equal to beta, or just less than beta, then we choose this term as alpha itself. Otherwise, we choose beta. Okay. And for the error, okay, so here actually um, so where is phi r plus alpha beta? So beta is here. Okay, phi r. Yeah. So actually phi t plus alpha here is considered as a target. Okay. So error usually before you see that error can be defined as phi target minus phi instantaneous. Okay. Usually defined this way. But now we use intermediate direction instead of using phi ref. We use phi r plus alpha, which means we use phi t. We use phi t minus phi of t. Okay, we use this one instead. Okay, we don't use phi reference, but we use phi t. Use phi r plus alpha or phi r plus beta. It's just phi t in different case. And then we can construct controller. This one is controller. Okay, that is a feedback. So we control the velocity according to the error from the current position to the target. So here let's see an example. Write a control algorithm for differential type robot to achieve the reference pose. This is the goal: 4 meter and 0 degree. Using the presented control to the reference pose using an intermediate direction. First, here the example asks to find an appropriate value for parameter r. Okay, the initial pose of the vehicle is 1 meter 0 100 degree. So initial of the robot are more than 90 degrees, so it's like look like this. So actually look just like in this picture, right? 9 degree and then 9 degree plus 10, this is 100 degree. Look like this 100 degree. And the goal is 0, so it just look like this. Okay, the goal, the reference is 0 degree here. So test the algorithm on a simulated kinematic model. Okay, so use MATLAB script code. Again, similar to previous example, first we define sample time, set up the duration of the simulation from 0 to 15 seconds, and we need to update the value of controller at every sample time. Then choose distance r as 0.2. So this one answer this this the problem asks us to choose the learn. Now we choose this already. And q ref here, this one q ref. So q ref is actually h ref, y ref, and phi ref. And initial position, so Q start from initial and then Q update to be instantaneous. So in some sense, this one is Q0, okay, equal to 1, 0, and then 100 degree, which is 100 times pi over 180. This Q0, but after it's updated in the loop, it represent instantaneous. Okay, so QE at 0. So this loop over the period 0 to 15 seconds. First compute phi r. So phi r here. Phi r actually is just arctan of y ref minus y over h ref minus h. But here, instead of you arctan, MATLAB code also has arctan 2, which give the angle to be in the 4 quadrant. If we use just arctan like this, the return function will be in the first quadrant only. Okay. And then we can compute distance. Okay, distance d from instantaneous to goal. Okay, from instantaneous location to goal. Alpha is computed to be phi r minus phi ref. So here actually phi r minus phi reference, and we can check alpha. Where is alpha? Here, alpha. Okay, phi r minus phi reference, and beta is arctan r over d. So r is chosen to be, yeah, r is chosen, and then so beta this one. Can you see? Okay, this one is reference. And then here we need to assign the sign of beta correctly. So beta initially is calculated to be always positive, but then we check if the sign of alpha is negative, we invert the sign of beta. Okay. And for here we start to constructing the controller. So if absolute value of alpha less than absolute of beta, we define so here phi r plus alpha, here is phi t, actually phi t minus phi. So phi t of t minus phi of t. So this one is intermediate direction. This one is instantaneous direction. Okay. So this one is this one. Okay. So we can compute error, and then we can okay. So there are two cases. One is absolute alpha less than absolute beta. We use here, we use alpha here. Otherwise, we use beta instead. Okay. Yeah, actually also phi t, but in the case of alpha large, we use beta. Okay. In the case of alpha small, we use alpha itself. Small with respect to what? Smaller than beta. And then the linear velocity is alleged to be proportional to the distance from the instantaneous location to the goal. this one, and orientation velocity chosen to be proportional to the error. Okay, and this part just same as before at kinematic simulation using Euler integration. Okay, um, so the effect of velocity control, control law velocity, and control law of orientation from this equation, we expect that the motion of robot would be along this curve that start from the initial position here, move along this curve, and then finally it stop at the goal with orientation as we desire. Okay, any question? So let me just remind again. Once we know V and omega, we can use inverse kinematics and from robot velocity to actuator velocity. And then we have another set of control for the actuator. So in some sense, we are trying to generate desired velocity and desired orientation for the robot. And then we need to control the actuator such that robot will move along the desired velocity that we just chose. Any question, anyone? No. So this one is not difficult, both conceptually, both not difficult in terms of the concept and algorithm. And let's see the trajectory and velocity and orientation with respect to time. So trajectory here, h and in the h and y plane. So you can see start from here and then move along this trajectory and then it reach. Uh, yeah. So this one is a guiding point, means the switch between alpha and beta, I think. So controller is switch here from alpha to beta, and then finally it stop at the goal with the right direction, the right orientation. And yeah, here, so here we can see that we can see that the motion around here is almost like a line. Okay, so velocity somehow, okay, first it must move very fast, but the closer to the goal, the velocity fall. Okay, and for orientation, we can see that around here near the goal, the orientation change by a lot. So that's why we can see that in function of time, omega, direction omega, from around here, direction omega almost not change. It means from here to here. So from here to here, direction of omega, angular velocity, because here phi around here almost constant, right? From here to here. So no omega. It means angular velocity to rotate the robot is 0. But at here, it start at this corner, the orientation change a lot. So omega has certain value, and you can see that omega rotate in the direction of clockwise. So it fall to be negative, like this. But then when it's almost reached the goal, it's asymptotically approach to 0 and stay there, like this. Okay. So this algorithm seems very nice because the change of angular velocity is not much, and uh, algorithm is very simple. But for this algorithm, it can be applied to differential drive wheel, but cannot be applied to car like robot. Why? Can you give an idea, Sabun? The question is that this algorithm can be applied for differential drive wheel, but cannot be applied to car like robot. Yeah. Yeah, so it cannot rotate as much as we want, we can say, I mean, or not as much as the algorithm want, right? It must has constraint. So the curve here, the curve to rotate for the car is limited by a certain radius of circle, right? Yeah, so that is correct. And then here another algorithm that can be applied to both car like robot and differential drive wheel. So here is a control on a segmented continuous part determined by a line and a circle. Okay, line and a circle. So from the start here or instantaneous point here to goal here, we need to construct a circle with the radius that a car can move along the circle. Okay, this is the smallest circle, okay, that the car can move along. Um, so the line segment is to draw from instantaneous location uh, to the tangent point on a circle here. Okay. So from the start, well, actually, this point is not fixed. This point is not fixed because um, look, yeah. So phi t changed. Okay, phi t you can also change. It depends on the initial start. It because when robots move along around here, the tangent point can be different from this. Okay, so we define that the point for the tangent here is different locations, a little slightly different. Okay, so anyway, the idea is that in every instantaneous of in every instant, we need to find the tangent point on the circle. Okay, and we construct geometries like this to ensure that the robot move along the target lines. Yeah, to this we can say intermediate target before it switch to the motion on circle. So well, for the controller again we uh, define omega as a feedback, I mean proportional to the error between instantaneous orientation and the intermediate orientation. Now I call it intermediate because we don't use phi reference, but instead we use phi of t, and phi of t changed over time. As you can see here phi of t. So at any point in time, we can compute this point, okay, t y of t. So we can compute phi of t. So it must be different over time. So the idea is that when the distance to the intermediate point is small enough, the second phase begin, which means we switch the controller to be in a way that omega must rotate along the circle. So how can you achieve the trajectory along the circle? So on the on the circle, you need to have, well, you want linear velocity as v, okay, and then orientation, the angular velocity omega must be that velocity divided by the radius. It means angular velocity rotate along the circle, right? And this part is for correction in for some uncertainty. So this is kind of a feedback, okay, for correction when there is uncertainty or some error, okay, due to the dynamic of the feedback. And we can say that this part is feed forward, okay, and this part is feedback. Feed forward means we don't need to know the information of the location of the robot. We just make assumption that the robot is where it's supposed to be. So if it is there at that place, it should have a certain velocity, something like that. Okay, or certain angular velocity is feed forward. For the feedback, we need to know the information of robot's location. So in here we talk about orientation. We need to know the instantaneous orientation of the robot, and then we find the error between instantaneous orientation and the target orientation. And from this error, we design we make a desired angular velocity. So this is a feedback. Knowing the current value, and then we uh, recalculate the value of desired angular velocity. Okay, so it's in the loop over sample time. Okay, any question at this point? Okay. Well, the idea itself is very simple. It seems very easy, right? But when we make the algorithm, actually, the reference here I show does not show any algorithm, and I think it will take so much time. But the point is that if you understand what should be the input, what should be the output, that you can be used for some for other purpose or for extended application, then you have all the material for that. But if you want to understand a very detail, you need to look at the algorithm from response. I guess, yeah, there should be reference. I think from 3 to 5. Yeah, maybe you can find from 3 to 5. So here I try to explain some concepts as much as possible. So first, let me just raise out the problems uh, that ask us what to do. Okay, before I explain the code here. So in this example, it asks us to write a control algorithm for a differential type robot to achieve the reference position. Yeah, it's just same as before. Uh, the reference at 0, 0, 0 using control algorithm proposed in this section. The radius of the circle should be zero point 0.4 meter. Okay, so this is seems for very small robot, and the circle is very small. The initial position of the vehicle is at -3, -3, and 0 degree. Okay, so actually -3, -3. Let's say this is coordinate of x and y. So let's say, yeah, -3, -3 is here, and the initial orientation of the robot is like this. Okay, and then we want it to be here at 0, 0 with this direction. Okay, so it moved from here to here. So it moved in a certain way that before it reached the goal, it must move along a circle, arc of on the a segment of a circle with radius zero point 0.4 meter. All right, so yeah, actually the basic idea of the control algorithm is simple, but the implementation is not. Okay, so here I will try to explain, yeah, some terms, um, because in practice, some term for writing the code could be very different from what you have experienced. Well, so again, first we define sample time, duration of simulation, radius, distance parameter. This is distance parameter. This is not radius. Actually, yeah, distance parameters. So here is the reference formula. Oh, I think I think yeah, reference actually this one formula 0 here, and initial, where is initial? Let me see initial q here 1, 0. So I think it's yeah, it's different, eh? Oh, I guess I take the a different part. 3.4 and this 3.5 different thing, eh? Different thing or same thing? Let me see. Let me see. Different thing or the same thing? Why parameter different? Lead 3.4. That's okay. That's correct. Lead 3.4 is yeah. So actually here there is a mistake on the code for the reference. It's, it is 4 meter, y is 4 meter, and the initial portion 1, 0, and 100 degree. Okay, so not like this one, eh? So this one is 0, this one is 0, this one is 100 degree. That's fine. All right. Okay. So in here, actually, the algorithm or the code here also account for acceleration, maximum velocity. Okay. So when it needs to slow down and when it need to accelerate. And so here, maximum acceleration is defined as 5 meter per second per second. Maximum velocity is zero point 0.4 meter per second. Accuracy. What is accuracy? Accuracy here is Vmax time, sample time. Why this is accuracy? Because we update the value or update everything in between the sample time ts. So let's say if the robot is in moving at the maximum speed, before we check the location another time, it move it move at the distance of v maximum time sample time, right? So let's say at this moment it almost let's say it almost arrived the goal, like for example the error is 0.0001, let's say. So then because the time is not yet arrived, we don't update the value of v value velocity, then it still have full speed at v maximum. Then a certain sample time later we check the location and then it already passed the target point by Vmax time Ts. Right? You got the other point. And the curve zone here is the radius of the circle. So 0.6 actually say here say 0.4, so actually it's supposed to be 0.6. And then um, and here curve zone divided by 2, it means half of the radius. So R here is half of the radius. So I think this one maybe supposed to be diameter. This one is diameter. And this one is supposed to be radius. Okay. And 0.99 is just to um, how to say, we don't use 1, we use 2.99. It just, well, how can I say about this? Well, so this is not it's not so big deal. 0.99. Well, let's say this is 1, and we continue to the next. the items. Okay, so here initially the flag variable slowdown is set to 4. So I mean there must be cases that we want the robot to slow down and the cases we want robot to accelerate. Okay, and set the initial velocity as 0, angular velocity as 0. And here the matrix H here is for rotation by 90 degree. So H equal to 0 and minus 1, 1, 0. So this is rotation by 90 by minus 90 degree. Why? Because I can rewrite this cosine of minus pi over 2. Here is sine of minus sine of minus pi over 2, and here is sine of minus pi over 2. Okay, and here cosine of minus pi over 2. Okay, so we can see that it actually is rotation matrix by 90 degree. Okay, and here finish finish unit vector. This is finish unit vector defined by cosine of phi ref and sine phi ref. So for the vector defined by phi reference, then this unit vector, because the angle is this, unit vector has a component cosine and sine. And D is the destination points at the goal point here. So here I have here. So D is here, destination point. Phi ref, so we compute cosine and sine, we get a unit vector for this one. So this is a unit vector. The destination, S is instantaneous robot position. So for example, if robot is here, so S location of robot. And M is half of distance from S to D. So the midpoint, sorry, so midpoint is here. Yeah, is midpoint. And OV is the unit vector of orientation of the robot location. So if I have origin 0, 0 here, so let's say origin 0, 0 here. So from the origin to this point, I can construct unit vectors like this. So actually it's phi. Yeah, it's phi of t. Okay, so this one is phi of t. Okay, and this one SD vector means the vector from S to D, from here to here, and so vector from S to D, right? From S to D. I think I have explanation here as well, right? But yes, so I think I can explain here better. Yeah, I have graph. Right. Again, so D is destination, S is location of robot, is midpoint, and orientation, this vector, and then SDV vector from S to D. All right, and then L2 is the norm, which means the distance from S to D. This is L2. And I want to explain another terminology about rotation before we take a break. Cross product can be computed by a different way. If we have two vectors in a plane and we want to operate the cross product, we can actually rotate one vector by minus 90 degree and time and apply dot product to another vector. Then the value must be the component of the vector of the cross product. Okay, I think I should draw like this. So if I have a plane x and y, and I have two vectors in the plane x and y. Let's say this A, this is B, and I want to apply A vectorial B. What I do is, okay, I will get C vector C like this, and this vector C component must be it has component on z axis only. So C here only has z component. Let's say 0 0 CZ like this. So this component CZ I can compute by a different way. By actually I can use just A scalar B rotated by 90 degree. Okay, are you familiar with this? I will get CZ as well. Are you familiar with this? So vector A and B can get vector C, which is along the z-axis. So it means it has only z component. To find this z component, I can use a different way. I just rotate B by minus 90 degree and use dot product with A. I can get this one. Yeah. Uh, no, rotate B because B only on the H and Y plane, so rotate with respect to Z axis. So it's like this. So if I have B like this, it has component H here, BH here is B, I call it B1, okay, and component Y here I call it B2, right? So when I rotate 90 degrees like this, so component on H is just it's B2, and here is minus B1, right? So yeah, so this one is obtained from rotation matrix 0 minus 1 1 0 times B1 B2, right? So I can get what B2 up here and then minus B1. This is rotation by minus 90 degree, right? Then just use dot product of this vector with A, we can get component C. So let's check if I multiply by A transpose, so A1, A2 with the rotated 90 degree of B, so I can have this one is A1 B2 minus A2 B1. You see, this is the third component of cross product. A and B, right? You have A1, B1, A1, A2, A1, A2, 0, and cross product with B1, B2, 0. So I cross product it, I get 0, 0 here. So here I get what? Like this, A1, B2 minus A2, B1, right? A1, B2 minus A2, B1, right? So this same as this. So first rotate B by minus 90 degree, and then you scale up dot product with A. So in some sense, it's the operation is less, not so many. If you use cross product with three dimension, operation can be larger. So instead, this algorithm uses a different way, right, of cross products. Okay, I think we can take a break about 7 minutes. So we resume at 25 past 10.